This is section 12.5, the Binomial Theorem. So this is all about raising a binomial to a power. So something like x plus y to a power, like 0. So what I'm going to start out doing here is raising x plus y to various powers so that we can maybe find some patterns. So I'd like for us to do this, and I'm going to write them in sort of a strange way to start with so that you get a sense of what I'm looking for in terms of patterns. Okay, so of course anything raised to the 0 is going to be 1. And so this first answer is 1. Then x plus y to the first, of course, is itself. So that's 1x plus 1y. Like I said, I'm writing this in a particular weird form for something I'm wanting you to notice. Of course, that would simplify to be x plus y, but that's not what I'm hoping for you to look at. All right, so x plus y squared. Well, that is 1x squared plus 2xy, and if you're not understanding where that's coming from, think about writing x plus y times x plus y and multiplying those, perhaps using something you call FOIL, and it ends up simplifying to be this. Then if you were to take that answer and multiply it by another x plus y, let me remind you how to do that. If I'm multiplying x squared plus 2xy plus y squared by x plus y, I'm going to multiply x by everything up above. So x times x squared is x cubed, plus x times 2xy is 2x squared y, and x times y squared is xy squared. Then I'm going to multiply y by each of those things up there. Y times x squared is x squared y. Notice I moved over one place so that the like terms will line up. Then y times 2xy is 2xy squared. And then finally y times y squared is y cubed. And then adding those together, that's x cubed plus 3x squared y plus 3xy squared plus y cubed. So that means our answer is 1x cubed plus 3x squared y plus 3xy squared plus 1 y cubed. Okay, so if you go off to the side, maybe pause this recording and multiply that last answer by another x plus y, and then once you have it, write it down and come back here and see how you did. So pause it now, do that multiplication, and then come back in a minute. You should have gotten 1 x to the 4th plus 4 x cubed y. Whoops, messed up something there. Wanted that to be written in a certain way, so please pardon my sort of neurotic tendency to want the color thing to work for our benefit. So plus 6x squared y squared plus 4 xy cubed plus 1 y to the 4th. So let's look for a pattern. Well, for each answer, one of the things you might notice is, let's look at x plus y to the 4th, the last one we wrote. Every single term of that, and there are 1, 2, 3, 4, 5 terms there, every single one of those terms is degree 4. Remember, the degree of a term is the sum of the exponents on all the variables. So it's a 4th degree term, and then the next one is 3 plus 1, 4th degree. The next one is 2 plus 2, 4th degree. The next one, 1 plus 3, is 4th degree. And y to the 4th is 4th degree. And every term in there is 4th degree, and look at what you did to get there. You raised x plus y to the 4th. And so if you look at every line, that's true. For x plus y squared, every single one of those terms is quadratic. X squared, 1 plus 1 is 2 for xy, and y squared is quadratic as well. Okay. The next thing I'd like for you to notice is that there is one more term than the power. Like x plus y to the 4th has 5 terms. X plus y cubed has 4 terms. X plus y to the 0 has 1 term. So the power you're raising it to plus 1 is the number of terms you're going to have. Another pattern I'd like for you to notice is that the very first term starts with 1x to the power of the problem. So like in the last one we did, since it's x plus y to the 4th, the first term is 1x to the 4th. Then if you look at the powers of x from term to term to term throughout that answer, the powers of x start at 4 and go down to 3, then 2, then 1, and in the last one it's actually x to the 0. So the powers of x decrease throughout the polynomial answer we're getting. Now look at the powers of y. They start out in the first term being y to the 0, which is an invisible 1. Right after 1x to the 4th is y to the 0. Then it's y to the 1st, then y squared, then y cubed, and y to the 4th. And notice that the last power of y, 4, is the same number as what you were raising the binomial to, x plus y to the 4th. So that seems to make a whole lot of sense. So I'm thinking that with x plus y to the 5th, instead of actually doing the multiplication, let's see if we can get it right. So I'm going to look at the powers of x first. The powers of x will decrease. So the first one will have x to the 5th, the next one will have x to the 4th, and I'm leaving spaces for other things that are going in there, so don't squeeze this up too much. The next one will be x cubed. The one after that will be x squared. The one after that will be x, and the last one won't have a visible x because it's x to the 0. Okay, now the powers of y start at 0, so y to the 0 for the first term is x to the 5th times 1, then it'll be y to the 1st, then y squared, then y cubed, then y to the 4th, and finally y to the 5th. And every single one of those terms is degree 5. 5, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, and 5 all have degree 5. Now, the patterns we've already established, those that we just wrote down, those are pretty easy to understand for most folks. The next question is, what are the coefficients? Well, it seems like we always start with 1, so that's a good thing to start with. And it appears that the second coefficient, let's look up a row above, is 4. That number is the same as the power of x plus y to the 4th. That first coefficient, the second coefficient is 4. In the line above, x plus y cubed, the second coefficient is 3, etc., etc. So it seems reasonable to think that this is going to be 5. And if you look all the way to the other side, it seems that there's some kind of symmetry going on here. So we have 1y to the 5th and 5xy to the 4th. Now, the only question now for us is, what are the coefficients of the remaining ones? And so if you'll pull aside just the coefficients, this is called Pascal's triangle. By the way, this has a name. And what you need to do is see if you can find a pattern to build that up. And so we already know this is 1 and 5, and that's 5 and 1 at the end. What will it be in the middle? Well, if you've seen this before, or if you've seen it here because of what you're noticing, you might notice that any two numbers in a row added together give you the answer right below and between them. So like 3 plus 3 gives us 6. 2 plus 1 gives us 3. 1 plus 4 gives us 5. So 4 plus 6, that's a 10. And 6 plus 4, that's a 10. So going back to the answer here, this should be 10, and this should be 10. Okay. All right, so see if you can write the next one. I'm not going to change colors this time because that's a real big pain in the butt, to tell you the truth. So just did that for illustrative purposes, of course. So x plus y to the 6th. See if you can get that. So pause, see if you can get it, and then come back. Okay, so that's 1x to the 6th. I'm going to dispense with writing the 1 in front. 1 plus 5 is 6. X to the, decrease the power of x by 1, increase the power of y by 1. Plus 5 plus 10 is 15. Decrease the power of x by 1, increase the power of y by 1. Plus 10 plus 10 is 20. Decrease the power of x by 1, increase the power of y by 1. The next one is 15. Decrease the power of x by 1, increase the power of y by 1. The next one is 6. Decrease the power of x by 1, increase the power of y by 1. Plus 1, x to the 0, which is 1, times y to the 6th. And there's the last one. So the binomial theorem is going to allow us to get those coefficients and powers of x and y to produce this series. I don't know if you noticed that each answer is a polynomial, a sum of a bunch of things. It is a part of a series. Okay, so that's of interest because it kind of puts us back in the realm of what we've been talking about. So now that we know how to get Pascal's triangle for relatively small powers of x plus y, like up through x plus y to the 6th, you could certainly make Pascal's triangle like we did and get those answers and figure that out. The problem is that what if I said, okay, let's skip to x plus y to the 12th? That would mean you'd have to build Pascal's triangle all the way down to the level where the beginning of the line was 1/12. something and ended with 12, 1. And that recursive thinking is actually going to get in our way for bigger n, because we're not going to be able to really do that. It's not feasible to do that to that extent. So we're going to have to find a better way to get those coefficients. So to do that, I want to introduce to you something that's used in counting. It's called n choose r. And it's written like this. This is not a fraction. It's n and then an r below it inside parentheses. And again, the way you read that is n choose r. N choose r. And the calculation of n choose r is n factorial divided by r factorial times n minus r factorial. Let me remind you what n factorial means. If we have like 5 factorial, that means we multiply 5 by all of the positive integers from it down to 1. So 5 times 4 times 3 times 2 times 1 is what 5 factorial is equal to. And that's 120. Okay? So that's the formula for n choose r. The reason it's called that is, for example, if you had 52 cards in a deck of cards and you choose 5 of them, doing 52 choose 5 says how many different 5-card hands are possible if you have 52 cards and choose 5 of them. And so that would be 52 factorial divided by 5 factorial times 52 minus 5 factorial. Now I want to talk to you a little bit about factorial arithmetic. I'm going to use a smaller set of numbers. Like if I had 6 factorial and asked you to divide by 4 factorial. Since 6 factorial is 6 times 5 times 4 and the rest, I can stop that factorial anywhere as I expand it and just say and the rest, meaning factorial. So 6 times 5 times 4 factorial is 6 times 5 times 4 times 3 times 2 times 1. And I stop there because that's the number that matches the factorial in the denominator. So what you'll do is you'll take the larger of the two numbers in a fraction like this and start expanding it until you get down to the value of the smaller one. Stop, put factorial on it. Then those cancel. 4 factorial cancels, leaving 6 times 5, which is 30. So see if you can figure out the 52 factorial, etc. over there. See if you can do that. I'll give you a few minutes to do that. So pause the recording and see what you can get. Okay, hopefully you're back and have tried that. So the first thing I'm going to do with this one is, of course, order of operations says I should do everything inside the parentheses I can first. And 52 minus 5 is 47. And so looking at the two large factorials, I'm going to expand the largest one out, at least for a while. So 52 factorial is 52 times 51 times 50 times 49 times 48 times 47, stop, because that matches one of the factorials down in the denominator. So I'm going to write that one down here, 47 factorial. And the other factorial that's still there, just go ahead and expand it out. So 5 times 4 times 3 times 2 times 1 for the 5 factorial. Okay, so let's do some canceling. And I'm going to draw some lines through, but be careful that you don't obliterate what is there because I would want to see what you had here. So if you draw a line through that, like that, real faint line, that's good. You can tell that you're canceling, but it's not such that I couldn't read it. So in other words, I look over to the right. I don't want you to do this. I can't tell what that was if you do that. So please don't do that. Just a nice fine line through those. I'll write a little note here. Don't do that, because it makes it really hard to look and see what you had there. So hopefully you still remember what was there or wrote it down earlier, because it's gone now. Okay. Now some other things you might see is, for example, 5 goes into 50 evenly. So I could cancel that 5 and leave 10 up there. 4 goes into 48 evenly, 12 times. 3 goes into, see, 12, sure, 4 times. And 2 goes into 10, 5 times. And of course there are other numbers I could have chosen. It wouldn't matter which ones I chose. But at any rate, the stuff that's left after all that canceling is 52 times 51 times 50, which became 10, which became 5, times 49, times 48, which became 12, which became 4, all over 1. Okay, all of those ones multiplied together in the denominator are 1, and anything divided by 1 is itself. And so we're left with that multiplication to do, which if you didn't have a calculator would still be kind of a pain in the butt. I get that. But I'm going to show you a shortcut here in a second. But I want you to know how to do factorial arithmetic, like what we just did with all that canceling, because I think that's helpful for you to understand how a person could arrive at an answer. Anyway, if you multiply all this out, you get 2,598,960. That's the total number of different 5-card hands that exist. There are that many that exist. Starting with 52 cards. Pick any 5 cards at random. There are about 2.6 million different combinations of cards that you could get. By the way, that's also, sometimes you'll hear someone say combinations here, which makes sense. You can combine, well, I could get this to work. There we go. There are 2.6 million or so combinations of cards possible when you start with 52 and pick any 5. So let's see if we can make this a little bit easier. On your calculator, you're going to need to probably look for a factorial button. And everybody's calculator is different. You might have to Google your calculator and find out how to do factorial. But you're going to look for something like n factorial or some other letter factorial. It could be x factorial that you're going to want to look for. And so if you're going to do 52, choose 5, you would want to type 52 and then get that factorial and then divide it by. Then you'll need a set of parentheses to protect the denominator. So then 5, then go and find factorial again, times 47. I'm going to do 52 minus 5 in my head. 47 factorial, close parentheses, and you should get that same number that's close to 2.6 million. All right? So try that. Pause this and try to type that on your calculator, then come back when you've been successful and you get that 2,598,960 number on your calculator. Okay, then after you've done that, there's an even faster shortcut. Look for something that looks like this, NCR. That's the number of combinations given n things chosen r at a time. So that's n choose r. That C is for combinations, but if you say choose, it sort of makes sense. So if you type the 52, the number of things you have, and then pull up that NCR command, and again, you may have to Google this on your computer to find where on your calculator to find that NCR. You may have to, once you have your calculator, you might have to search for combinations. It'll be in the set of things called combinations and permutations, and you want to look for the command that gives you the combinations on your calculator. Typically, you have to type the n number first, then type that command, and then type the r number second. And so try typing 52 NCR5 in your calculator and see if you get that 2.6 million number, or close to 2.6 million. Okay, so pause the recording, see if you can do that, and then come back and see if you get the right answer, that 2,598,960. All right. So what does this have to do with the binomial theorem? Well, before I can answer that, before I want to answer that, I would like for you to do a few more of these. Do 6 choose 2. And I'd like for you to do these longhand, the way that we did those just a minute ago, because I want you to see what's going on and notice things about what the answers reveal to you, because they're important answers to know about. So again, don't use your calculator for these. Try to do it without a calculator. And then if you want to check yourself with a calculator, great. So I'll do the first one with you, and then I'll ask you to pause, do the other two, and then come back and see how you did. All right, so 6 choose 2 is by definition 6 factorial divided by 2 factorial times 6 minus 2 factorial. So that's 6 factorial over 2 factorial times 4 factorial. Expanding the greatest one of those, 6 times 5 times 4, stop, because that's equal to a factorial in the denominator that would cancel. So those will cancel. And then expand the other one. 2 factorial is 2 times 1. Then do the canceling. So the 4 factorials cancel, leaving 1. 2 cancels with 6, leaving 3. So you're left with 3 times 5 times 1 divided by 1 times 1 times 1, which is 1. And so you're left with 15. Okay, pause the recording and see if you can do the other two. Okay, hopefully you actually did pause the recording as I asked you to do, because this is something I would like for you to be able to do. So 8 choose 0 is going to be 8 factorial divided by 0 factorial times 8 minus 0 factorial. Which is 8 factorial over 0 factorial times 8 factorial. And you probably see that the 8 factorials cancel, leaving 1 over 0 factorial times 1, which is 0 factorial. Now, I think I said this earlier, but in a few sessions ago, but 0 factorial is defined to be 1. So that's 1 over 1, which is 1. Okay, and then 10 choose 10 is 10 factorial over 10 factorial times 10 minus 10 factorial. So that's 10 factorial over 10 factorial times 0 factorial. The 10 factorials cancel each other out, leaving 1 over 0 factorial. Since 0 factorial is 1, 1 over 1 is 1. Okay. So this time I'd like for you to go back and do those problems in your calculator using that NCR function and see if you can type like 6 NCR2 and get 15, and 8 NCR0 and get 1, and 10 NCR10 and get 1, to reconfirm that we've done these correctly. Okay, so as it turns out, this is the connection to the binomial theorem. To get those coefficients, instead of using Pascal's triangle, always, this is how it works. The first one is x to the nth. The next one will be n, choose 1, x to the n minus 1 times y to the first. And I probably should go back and explain that first term better. So go up here to the right, let's look at that. That's technically n, choose 0, x to the n minus 0 times y to the 0. Okay? And so in the next one, the 0 turns into a 1. And that's how you get all those things. For the next one, it'll be n, choose 2, x to the n minus 2, y squared. And hopefully you're seeing the pattern. What would the next one be? N choose 3 times x to the n minus 3 times y cubed. Then the general term is n, choose r, times x to the n minus r times y to the r, plus dot, 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 plus the very last one, which is well, I'm sorry, the penultimate one, I should say. Let's do it first. The penultimate one is n, choose n minus 1, x to the n minus n minus 1, y to the n minus 1, plus n choose n, this is the last one, x to the n minus n, y to the nth. Okay. And so these last two terms, just the last two terms, to give you the simplified version of them, n minus 1 is going to be x to the first, y to the n minus 1, and n choose n. N minus n is 0. X to the 0 is 1, leaving y to the nth as our last term. Okay, so that is the binomial expansion of x plus y raised to the nth. Now that's kind of unwieldy and not that easy to memorize. You might notice that it's always going to be in the form. See this general term over here that I wrote? That's the form that they're all going to take. N, the number n, will be the power of your binomial here. In the original problem, that's what n is that power. And r changes from 0 to 1 to 2 to 3, etc. until you get to n. The last one is n choose n. and that's the last one you do. And the power of x is n minus r, the difference of those two numbers inside the parentheses, and then y, the power of y is the lower of those two numbers. So, as it turns out, the binomial theorem can be written in a nice compact way. Let me write the beginning of it again. X plus y to the nth is a sum, right? It's a sum of things added together. And the thing that we're going to have change is r. And the value of r starts at 0. And again, you can look up here. This was that first term here, which is the same as that one, simplified. The r started with 0. Okay? Starting r equals 0 and ending when r is equal to n. And that's, again, this one, where the lower number is n. Of n choose r times x to the n minus r times y to the r. That right there is the binomial theorem. Okay, so you need to commit that to memory, something you have to be able to use and use correctly. Okay, so let's do an example of that. We are supposed to, in this example, take x plus y and raise it to the 9th. Okay, so that's 9, choose 0, x to the 9 minus 0, y to the 0, plus 9, choose 1, x to the 9 minus 1, y to the first, plus 9, choose 2, x to the 9 minus 2, y squared, plus 9, choose 3, x to the 9 minus 3, y cubed, plus 9, choose 4, x to the 9 minus 4, y to the 4th, plus 9, choose 5, x to the 9 minus 5, y to the 5th. And once you get going with this, and you've done a few of these, this is not that hard. It's kind of tedious. I get that. But each one of these by itself is not that hard. In fact, I can actually talk and do this at the same time, which means it's got to be pretty simple. I can barely talk and write at the same time. You've probably seen me make mistakes doing that. This is an easy pattern to follow. Once you get going, it's not bad. So 9, choose 8, x to the 9 minus 8, y to the 8th, plus 9, choose 9, x to the 9 minus 9, y to the 9th. Now, you're probably going to need to go to your calculator for some of these factorials expressions and choose R, that NCR command on your calculator. Do 9 NCR 0 and 9 NCR 1, etc. And do all of those. And when you complete that, you should get 1 x to the 9th times 1 plus 9 x to the 8th y plus 36 x to the 7th y squared plus 84 x to the 6th y cubed plus 126 x to the 5th y to the 4th plus 126 x to the 4th y to the 5th plus 84 x cubed y to the 6th plus 36 x squared y to the 7th plus 9 x to the 1st y to the 8th plus 1 x to the 0 y to the 9th. And there's the expansion of that binomial. Now, you can imagine, if I gave you a number bigger than 9, that's a whole lot of terms. For 9, it was 10 terms. And if I did x plus y to the 25th, I would probably have a mutiny. And so there is a way that these sometimes are asked so that you don't actually find all of them. And we'll do a problem like this a little bit later. But I could say, well, find the one of those terms that has x to the 5th in it. And so instead of finding the whole expansion, I would be looking for you to be able to find that one. Because I assume if I had you find that one and you could get it correct, you could find any of them. So when n is really big, that's the way the question will be asked. Is I'll tell you something about the term I want you to find, and once you've found it, that's the only answer I'll be interested in, not the rest of them. Thank goodness. Okay, so let's practice this a little bit more, because it's not always x and y. Sometimes those are replaced by other things, like a minus b over 2 to the 5th. Since the binomial theorem uses addition, I would like for you to think of that as a plus the opposite of b over 2. It's being raised to the 5th, because that way we can still use the theorem. Okay, so just keep in mind for this problem that wherever we had x before, that's now a. Wherever we had y before, that's now opposite of b over 2, and the n value is 5. Okay, so this is equal to, according to the binomial theorem, 5, start with 0, 5, choose 0. First thing, notice I'm not saying x, so I'm not even going to say a. First thing to the 5 minus 0 times the second thing, negative b over 2, to the 0. Plus, then it changes to 1, so 5 choose 1. A to the 5 minus 1, opposite of b over 2 to the first, plus 5 choose 2. A to the 5 minus 2, opposite of b over 2 squared, plus 5 choose 3, first thing to the 5 minus 3, second thing to the 3, plus 5 choose 4, first thing to the 5 minus 4, second thing to the 4th, and finally 5 choose 5, first thing to the 5 minus 5, second thing to the 5th. Okay, then simplifying, that's 1 a to the 5th times 1. Okay, so plus 5 choose 1 is 5. A to the 4th times negative b over 2 to the first is itself, of course. Then 5 choose 2. Yeah, that's where we are. 5 choose 2 is 10. A cubed, opposite of b over 2 squared, plus 5 choose 3 is 10. A to the 5 minus 3 is 2. Second thing, negative b over 2. You know what? I just thought about something. I had negative b over 2 squared already, and that same thing cubed already. So I'm actually going to come over here and start simplifying those. Since I had those powers already, I don't want to waste the time and take a whole nother line just to write that and then simplify it separately. So sorry about that, but I think this is going to be more in line with what I would want you to do. I don't want you to write 6,000 lines for this. So back to the one where it was a cubed. Negative b over 2 squared is negative b times negative b, which is b squared, over 2 times 2 is 4. Okay. And then a squared, you're going to have times negative b over 2 cubed. Negative b times negative b times negative b is the opposite of b cubed. Over 2 times 2 times 2 is 8. Plus 5 choose 4 is 5. A to the first because 5 minus 4 is 1. I'm not going to write that 1. And negative b over 2 to the 4th. Negative b times negative b times negative b. That's positive b to the 4th over 2 to the 4th, which is 16. And then finally, 5 choose 5 is 1. 5 minus 5 is 0. A to the 0 is 1. And negative b over 2 over to the 5th is the opposite of b to the 5th over 32. Okay, so I think this is the last line. Simplifying, that's a to the 5th minus 5 over 2. Notice I'm pulling the numerical part out in front. A to the 4th b plus 10 over 4 is 5 halves. Just pull that 4 out in front. A cubed b squared minus 10 over 8 is 5 fourths. A squared b cubed plus 5/16 a b to the 4th minus 1 over 32 b to the 5th. And so notice I rewrote those so that they were the numerical parts in front, the coefficients, times the power of a times the power of b, sort of in alphabetical order of variables, if you will, for each term, with a number in front, coefficient in front. Okay, this one is a little bit more challenging. We have 3 over, oops, let me write that again. That 3 didn't look very good. 3 over m squared minus 2 square roots of m raised to the 4th. And we're going to assume m is positive because we don't want to divide by 0, which is what the first one would have us do if m were 0. And we don't want to take the square root of a negative number. So we're going to make that assumption about m so that we don't get into any trouble with getting good answers. Okay, so according to the binomial theorem, the power is 4 choose start with 0 always. Then whatever the first thing is, 3 divided by m squared, that will be raised to the 4 minus 0 power. And the second thing, whatever it is, will be raised to the 0 power. Now notice I didn't write it this time, but that subtraction becomes plus a negative. So the second thing is a negative 2 square roots of m, just so that you're aware. Okay, the next one, now we're going to go up to 1, so 4 choose 1. 3 over m squared, the first item, to the 4 minus 1. And the second item, negative 2 square roots of m, to the first. Next one, now go up to 2, 4 choose 2. 3 over m squared to the 4 minus 2 times negative 2 square roots of m squared, plus, we're up to 3, so 4 choose 3. 3 over m squared to the 4 minus 3, and negative 2 square roots of m cubed, plus, now we're up to 4, and that's the last one. That's where you're doing number choose itself, 4 choose 4. 3 over m squared to the 4 minus 4, and negative 2 square roots of m, finally to the 4th. Okay, so let's see. 4 choose 0 is 1. 4 minus 0 is 4. 3 to the 4th is 81. And m squared to the 4th is m to the 8th. Remember, when you have a power on a power, you multiply the two exponents. So m squared to the 4th is m squared, m to the 2 times 4, which is 8. And negative whatever to the 0 power is 1. Okay, 4 choose 1 is 4. 4 minus 1 is 3, so 3 cubed is 27 over m squared cubed, which is m to the 6th, times negative 2 square roots of m, plus. Now 4 choose 2 is 6. 4 minus 2 is 2. 3 squared is 9. M squared squared is m to the 4th. 2 times 2 is 4. And negative 2 square roots of m squared is positive 4 m. Square root of negative 2, the square of negative 2 is 4. The square of the square root of m is m. Plus, 4 choose 3 is 4. 4 minus 3 is 1, so that fraction to the first is just itself. And negative 2 square roots of m cubed is negative 2 times negative 2 times negative 2 is negative 8. M to the, square root of m is m to the 1/2 cubed. 1/2 times 3 is 3/2. And then 4 choose 4 is 1. 4 minus 4 is 0. Anything to the 0 is 1. Negative 2 to the 4th is positive 16. Square root of m to the 4th is m squared. Okay. So, look for all the numbers in each term. 1 times 81 times 1 is 81 over m to the 8th. Plus, now the number is 4, whoops, got ahead of myself there. 4 times 27 is 108 times negative 2 is negative 216, so negative 216. And then m to the 1/2 divided by m to the 6th. To divide powers with the same base, you subtract, so 1/2 minus 6 is negative 11/12. Okay. Then 6 times 9 is 54, times 4 is 208, so plus 208. M divided by m to the 4th is m to the negative 3rd. And then 4 times 3 is 12. 12 times negative 8 is negative 96. M to the 3/2 divided by m squared. 3/2 minus 2 is negative 1/2. And of course 1 times 1 times that is just that. And that's a good answer. If you were not supposed to leave negative exponents, if that was kind of a forbidden thing, let me write a final answer that you might need to know is equivalent to the one we just wrote. So to get rid of that negative, we take it to the other part of the fraction, to the denominator in this case, to turn it into a positive exponent. So the last line is fine, and this line is better, because generally speaking we don't want negative exponents. And that m to the 1/2, if you wanted to write that as square root of m, you certainly could. It means the same thing as this does. I'm going to leave it like that. So that is the final answer for that problem. Now this is where it's important that you think about, if I say like the ninth term. Actually, let's start with it smaller. I'm going to use one that we already talked about. So the third term in the expansion of, let's make this easy, x plus y to the 5th. Okay, so we know that that's 5, choose 0 to begin with. X to the 5 minus 0, y to the 0, plus 5, choose 1, x to the 5 minus 1, y to the 1st, plus 5, choose 2, x to the 5 minus 2, y squared, plus the rest of it. I'm not going to finish it because I'm focusing on the third term. The third term. This is the first, this is the second, this is the third. And what I want you to pay attention to is, if I'm saying a particular term, like the third term, that means that this number r is 1 less than that. Okay? It's 1 less than that. So if I'm asking for the third term, that means r is 2. Okay? Third term, r is 2. Look at the second term, r is 1, 1 smaller than that. First term, what's r? 0, 1 less than that. So whatever term I'm asking for, if I say a particular term number like the 9th term, r will be 8. So that's important to know, to make sure you get the right answer. So for example, if I ask you to take the expansion of a plus 2b to the 10th, and I'm really hoping we don't have to write this one out, and find all 11 terms of it, because that's just, well, annoying. And I want you to find the 4th term. You need to realize that the only way that you're going to do that with any kind of ease, particularly if my numbers were bigger, like if that were a plus 2b to the 74th, and now we're asking you to find the 53rd term, or the relatively big numbers, you need to know how to do this in a generic way. So if it's the 4th term, that means r is what number? Right, 3. So n, of course, is 10, because that's the power on the binomial. So 10, choose. We just decided r was 3. 10, choose 3. Our first thing is a. That'll be raised to the 10 minus 3 power times the second thing, which is 2b, raised to the 3rd power. And now all you have to do is simplify. So 10 choose 3 is 120. 10 minus 3 is 7, so that's a to the 7th. 2 cubed is 8, b cubed. And when you do the simplification, you should get 960, a to the 7th, b cubed. You should never leave your answer with the second to last step here with that times 8 in the middle of the problem. All the numbers need to be brought out to the front. So, next question I want to ask you. I'm actually going to ask you several, so I think I'm going to go to another recording to do this. So I'm going to stop this one and go on to the next one.